Part D, the title, Modeling of Free Oscillations and Force Oscillations. So in this part, we will do some, application problems. D.1, mechanical mass spring system. Yeah. All right, first, let's look at the yeah, and let me see. Oh, yeah, the receiver. Oh, yeah, okay. Yeah, setting up the model. So let's look at the, the structure of the system. Yeah, all right. So here you can, spring a ball with a certain weight, motion thing. Yeah. So here, first, we study the spring. All right. The property, yeah, resists extension as well as compression. Yeah. Following the same rule, but direction different. Okay, extension, compression, different direction, but the basic rule is the same. Hooke's law. Yeah. F1, because in this system we may have multiple forces. Yeah. So F1, yeah, the resistance force, just one of the possible forces. Yeah. All right. Negative K constant times the displacement. Yeah. All right. K, spring constant, always positive. Yeah. The negative gave us the direction of the force. Yeah. So we need to define positive direction first. Positive, negative directions. Yeah. All right. Yeah. So the stiffer the spring, the larger the K. Yeah. So, student join us. Austin, Rami, join us. All right. Yeah. This is the direction. Okay. Yeah. Yeah. This going down. Yeah. This arrow. This is our positive direction. Okay, so we pull, yeah. So we, stretch, pull, down, yeah, positive direction. But the resistance, the force, opposite direction. Okay, yeah. When we move the ball down, there is a F1, pulls upward. Yeah, so opposite direction. That's why it's negative. But if you, compress upward, then the resistance force going down, yeah, opposite direction. All right. Yeah, so that's the positive direction for both force and the displacement. The displacement Y, we also use this as the positive direction. Force, also positive direction. Yeah. All right. So now we need to study the system. Force from the weight of the ball. Yeah, so there is another force, weight, force. Yeah, so we use F0. Yeah. All right. Yeah. So mg, the g, the constant of gravity. Yeah. Yeah. So the the unit here we use the meter per s squared. Not feet. Yeah. So here we use the meter system. All right. And little m, mass. Yeah. Yeah. And all right. Yeah. All right. Negative F0. Yeah. So the weight. Yeah. Weight direction. Yeah. Yeah. All right. Yeah. So then F0 has no effect, although this force exists. But if you study the whole system, the weight force always exists all the time. Yeah, right? Yeah. it applies to the whole system all the time, then we treat it as, because there is no change caused by, because for the moving part, after this balance, so let's assume, because here we apply the weight force, right? Then we treat this as the balanced point. Then where other forces are applied on the system, we can ignore the force of the weight. With respect to the balanced point. So for that reason, so later when we write ODE, so you will not see this weight force. Because you can think about, when we write ODE, left-hand side, right-hand side, cancel out. Right? So that Newton's second law. So first, Hooke's law describe one of the forces. But when you look at the motion part, you need to use the Newton's second law. All right. Mass times acceleration, m times y double prime. Acceleration. Double prime of this displacement function. Why is the displacement function? First derivative, that's velocity, right? So here we know the meaning of, from the displacement function, y function, when we take the first derivative, we get a velocity function. Second derivative, we get acceleration function. So that's from the physics. M times acceleration equals force. Here, the force here. The overall force. Because you have multiple forces applied to the system. So you need to combine all the forces. So that force. All right. So the force is the resultant of all the forces acting on the ball. All right. So we use Newton's second law, so we can write our ODE. All right. Next, ODE of the first we study undamped system. Second, then we study damped system. So undamped. All right. So this system, there is no damping force. Because for the damping part, there is another force, right? Slow down the motion. The damping force, we consider slow down the motion. But first, we study a relatively simpler case, undamped system. All right. Condition for undamped system. So let's apply Newton's second law to get ODE. Assumption. So when we consider undamped force, because in the real world situation, you always have the damping part in the real world. But in our modeling, when the damping is very small, so we ignore it. So we do not consider it. So we treat it as an undamped system. The motion of the system considered over a relatively short time. Second assumption. Relatively short time, short period of time. So from this second assumption, you can see the damping force is applied to the system. So first, very short. Second, apply in a short period of time. So the impact is very small, so we can ignore it. Yeah. So under these two assumptions in the real world situation, we can simplify our system to this undamped system. All right, now let's apply Newton's second law and Hooke's law to establish the ODE. Yeah. All right. Yeah, that's simple. Okay? Yeah. Yeah. Because there are only two forces, right? Yeah. Think about, this part, the force part, we should move to the right hand side, right? Yeah. Right hand side, negative K. Yeah. Hooke's law. F1. Yeah. The force. Yeah. Newton's second law. By Newton's second law. Right hand side, the second force, right? Yeah. So F1. Yeah. So if I write a little bit. Yeah. But you can see it easily. Yeah. Yeah. Because here I already changed the form. Yeah. The original form, right hand side should be the force part. Yeah. But the force part, by Hooke's law, negative ky. Right? Yeah. Then the negative term here. Oh. Yeah. Yeah. We need to. All right. So right hand side term, when we move to the left hand side, so we get plus ky. Yeah. All right. Yeah. That's the standard form. Then we, divided by n, so we get that standard form. Yeah. Very simple. Second order ODE. Yeah. We learned how to solve this simple ODE before. Yeah. Yeah. So because we have formulas, A constant, B constant. Yeah. But for that one, A equals 0. Yeah. A equals 0. Okay. Yeah. All right. So B, K over M. Yeah. So we can look at the solution. Then, in order to write the solution, yeah, we need to look at the discriminant. Yeah. Because for the positive discriminant, negative discriminant, the solution forms are different. All right. Let's look at the discriminant. A squared minus 4b, yeah, it's a negative one. Discriminant negative, that means the two solutions, basis, remember the basis, two solutions, sine, cosine. Yeah, negative. Positive, e functions, right? Yeah, positive e functions. Negative sine, cosine. Okay, all right. So here, yeah, but the A, yeah, so there is A part, but A is 0. Yeah. So this E function part becomes 1. Yeah. So Y1, Y2. Yeah. All right. Then omega 0. So here, yeah, because this expression, square root of K over M, yeah, we want to use a simpler symbol, omega 0, to represent this constant. Yeah. Then we can write a general solution for this undamped system. Yeah. That's sine, cosine. Okay. Yeah. With two constant, capital A, capital B constant, and there is an omega 0 constant inside cosine and a sine function. Yeah. Yeah. Omega 0 is known, yeah, because from given k constant and given m, so the omega 0 is determined for the system. Capital A, capital B should be determined by initial conditions. Yeah. So here we do not have initial conditions. Yeah. So later we need to, when we have initial conditions, Yeah. So the, y, for example, y of 0 given, y prime of 0 also given, so we can find capital A, capital B. Yeah. All right, constant. But then this omega 0 has some special meaning here. Yeah. All right. First, the period. Period. Remember last time we calculated the period. Yeah. 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 Remember how to calculate period. Yeah. We know cosine function is a 2 pi periodic function. 2 pi cosine function. Yeah. All right. So if we add 2 pi on top of this omega 0 t, same value. All right. But in order to get a period, we need to factor out omega 0. So inside the parenthesis p plus 2 pi over omega 0, we get a period. Okay? We get a period. Yeah. Yeah. All right. Then frequency. Yeah. Frequency is the reciprocal of the period, right? Yeah. Frequency. So the period and frequency, the relationship, reciprocal of each other. Yeah. So the frequency of the system is omega 0 over 2 pi. Right. Yeah. So that's the basics of this system. Yeah. And we give a special name to this frequency expression. Natural frequency of the system. This system has a natural frequency. Yeah. Yeah. Because later we will consider some external force applied to the system. Well, here there is no external force. Only internal force, external. So you need to, have some other forces. Yeah. But when you apply external force, the force could have some frequency. Yeah. The force function could have a different frequency. So this natural frequency for this one. Yeah. So then there is another frequency for the external force. Yeah. So we need to consider, the impact of external force. Yeah. Related to the natural frequency. Yeah. So later we will study that phenomenon. Yeah. All right. So here, that's the basic information about this undamped system. Yeah.
What is omega naught in this again?
Omega naught we define as root of k over m.
Okay.
Yeah. Yeah. Just write our general solution in a clean way. Yeah.
Okay.
Yeah. If you put this whole expression here, it's okay, but because it's more convenient in our discussion, so we use omega naught. Yeah.
I thought I remembered it having a name or something. Never mind. That's fine.
Yeah. Yeah. So,
Is it? Okay.
yeah.
Well, yeah. Oh, yeah. Okay.
Yeah. Some angle thing. Right. Yeah. All right. Yeah. Then next we study the damped system. So this time we need to add another force, from the damping part. Yeah. So this time, you can see we add some extra, because here we do modeling, simulation, right? Yeah. So this small device, so we use to simulate the damping part. Yeah. All right. Then we need to modify our previous system by adding a damping force. Yeah. So the damping force here, we need to make some assumption. Yeah. So F2 equals negative CY prime. Why prime velocity function, right? Yeah. So here you can, yeah. So we use another rule, yeah, about the damping force. Yeah. C is the damping constant. Yeah. You know, direction opposite. Yeah, because you reduce the motion, right? Yeah. So you slow down. Yeah. You're using this force to slow down the motion. So the force direction is the opposite direction, negative. All right. So we assume this damping force to be proportional to the velocity. Yeah. Proportional to the velocity. A good approximation for small velocities. Yeah. If the velocity is relatively large, then the approximation won't be good. Yeah. This modeling method won't be good. Yeah. So, but under the small velocity condition, yeah. So this modeling is very close. Yeah. All right. Then ODE of the dampened mass spring system. This time we add one more force to the right hand side, right? Yeah. Right hand side because we need to combine all the forces at the right hand side for Newton's second law. Newton's second law. So we add one more. Yeah. But that negative cy prime, after we move to the left hand side, becomes positive cy prime. Yeah. So you can see this damping force corresponds to the y prime term. Yeah. We just add a y prime term. Yeah. And we know how to solve this ODE. Yeah. Yeah. A constant, B constant, right? A constant, B constant. Yeah. We have the formula. Yeah. All right. The standard form, yeah, AB, yeah. Yeah. So we can, write it as in the standard form. Then, yeah, first we calculate the characteristic equation, right? Yeah. So this lambda square characteristic equation of this second order ODE. Yeah. So we apply the quadratic formula. Yeah. Yeah. Here we can look at the discriminant a square minus 4b. A square, a square, yeah. Oh, a is this one, right? Yeah. A square minus 4b. Yeah. All right. So this is the discriminant. Then we need to do a discussion on this discriminant expression. Yeah. Positive, negative, or zero. Yeah. Three cases for the discriminant. Case one, where the discriminant is positive. Yeah. Only look at the numerator. Yeah. All right. Positive. Yeah. So we call it over damping. Yeah. So this system, give it a name. Over damping. Okay. All right. Yeah. All right. Yeah. But in our later formulas, in order to make the, our formula clean, yeah, neat, yeah, so not very messy, yeah, because a lot of formulas could be very complicated. So we introduce two constant expression, alpha and beta. Alpha, C over 2m, beta, that relatively long expression. Then we can use alpha beta to represent our general solution. For case one, the general solution is C1 times e to the negative alpha minus beta t C2 plus beta t. Yeah. All right. Yeah. So relatively compact form for the solution. Case two, discriminant equals 0. Yeah, so you have, your quadratic equation has double real root. Yeah, so one real root, but it's a double root. Yeah, so you know the meaning. Yeah. Yeah, so this case we call the critical damping. Yeah. The critical damping, all right, system. Then its solution, yeah, we know, yeah, we have the form because beta equals 0. In this case, beta equals 0, so we only have the alpha part, C1, C2. Yeah. C2, there is a T. Yeah. Yeah, so that structure. All right. Case 3, yeah, less than 0, discriminant. So this system we call the under-damping system. Yeah. Sine, cosine. Yeah. So this case, sine, cosine. Yeah. Yeah. For some omega star, yeah, because here we need to use, some special constant. So omega star equals this expression. Yeah. Yeah. So you can see, yeah. Yeah. But different from that beta, slightly different from that beta. So we will rather use another symbol, omega star. Yeah. Yeah. So in this way, so you can also solve that damped system. Yeah. All right. Yeah. Not too hard. Yeah. But you need to, when you do the calculation, you need to be very careful. Yeah. Yeah. All right. Next. Yeah. D.2. From free motions to forced motions. Yeah. Free motion, no external force, right? Yeah? Yeah. No external force. Yeah. So all of the forces we treat internal force. Internal force. Okay. Yeah. So then, this time we consider external force. Yeah. So forced motions. Yeah. Another force. All right. Role of forcing function. Now we study the forcing function, external force part. Yeah. So then there is another, yeah, so external force applied to the system. Yeah. In both directions. Okay? Yeah. Sometimes positive direction, sometimes negative directions. Yeah. All right. Then, yeah, the free motion, the external force part is 0. Yeah. So right hand side, yeah, that corresponds to the external force term. Yeah. All right. Yeah, we call it homogeneous. Yeah. All right. Then, yeah, so no external forces, only internal forces, yeah, control the motion. Yeah. Now we consider external force. Use little r function represent that forcing function. So we put the r function at the right hand side. So it's a non-homogeneous ODE. Yeah. So this time, yeah, we need to solve this non-homogeneous second order linear ODE, but with constant coefficient for y prime term and a y term. Yeah. All right. Yeah. All right. That's forced over. Yeah. Then there are several names for this r function. Yeah. So one is forcing function. Yeah. Also, some people also call it input function, input output. Yeah. So this input. So yeah, because it's known. Yeah. External forcing function is given. Yeah. You apply it to the system, so people treat it as input of the system. All right. Or driving force. Yeah. Yeah. Then the solution, y of t function, yeah, that's the output. Yeah. Yeah. So you apply input, then you get output from the system. All right. Or response of the system to the driving force. All right. So that's the system. Then there is another. This time we need to study a very important phenomenon: resonance. Yeah. Resonance problem. So we need to model it. Yeah. Model this resonance. Yeah. So people observed, resonance phenomenon, causing a lot of damage. Yeah. But at the beginning, couldn't understand why, some unexpected, damage occurred. Yeah. Yeah. So then, there is a model should be used to describe this phenomenon. Yeah. All right, let's look at this model. And the resonance phenomenon occurs for a special type of external forces, periodic. When the external forces have this property, periodic property, then this resonance problem could occur. If non-periodic, then no resonance problem. Yeah. So based on this observation, yeah, all study, do experiments, yeah, based on that understanding. So we model the external force, R function, little r function, by a periodic function. Okay. F0 times cosine of omega t. Although you can add a sine term, yeah, but here we just use a simplified version. Yeah. Yeah. Later, if we want to add a sine term, yeah, we can add a sine term. Yeah. All right. Yeah. So we assume. Yeah. All right. So that this time we consider non-homogeneous ODE like this. Let's try to calculate solution. Yeah. Try to solve this ODE. Yeah. And we want to see under what condition that resonance problem occurs. Yeah. All right. D.3, non-homogeneous second order linear ODEs. Yeah. So we need to solve that system. Yeah. All right. Yeah. So this time we study. Yeah. Yeah. Actually, our previous system, constant, right? P function constant, Q function constant, much simpler. Yeah. 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 But here, the more general form is that. Yeah. The general solution. Yeah. So here let's review how to solve this non-homogeneous second order linear ODE. Yeah. Let's review a little bit. Yeah. We learned before. Yeah. So the general solution should contain two parts. Yeah. The first part, homogeneous. YH means the general solution for the homogeneous version of the equation. Yeah. So that's the H part. Second part, particular solution. Yeah. Particular solution, you only need to find one special solution for that non-homogeneous system. One is enough. Yeah. So you add these two solutions together, so you get the general solution for a non-homogeneous system. Yeah. So that's the, we did before. All right. The idea. stated before. All right. Then, the structure, first we consider the structure of the homogeneous part, YH function. That is the linear combination of two special solutions, but these Y1, Y2 functions form a basis. Should be a basis of the solutions. Homogeneous solutions. All right. So that basis concept. So then linear combination, the general solution. Right. So that's the form of the YH function. All right. Is the general solution of this homogeneous version of the equation. All right. A general solution of a non-homogeneous ODE includes all solutions. So this part, then YP part. Yeah. Yeah. But here, so there is a, so this statement, let me explain this, let me explain this statement a little bit, because it's related to singular solution. So I need to, I mentioned that singular solution before, but I feel, so probably you, most of you already forget the meaning of singular solution. So here, let me use 5 minutes to explain. Because here we have concrete example. Before, the first time I talk about the concept singular solution, I didn't give you concrete example. So I just mentioned a little bit. So you may not have a strong impression. So this time, I want to spend a little more time to explain this concept. All right. First, what is the singular solution? All right. Related to the general solution. So this concept related to the general solution. You know the meaning of general solution, right? By the logic, you can easily see, when we talk about singular solution, it cannot be covered by general solution. Otherwise, we do not call singular solution, right? So if a solution is covered by the general solution, then it's not singular. It's a normal solution, right? So the meaning of singular solution, very obvious. First, it is a solution. Second, you cannot derive the singular solution from your general solution. Okay? So what do you mean you derive singular solution? You can choose any C1 constant or C2 function you want. Okay? You have freedom to choose C1, C2 constant. But you can never get a singular solution. No matter how you choose C1, C2 constant, you can never get that singular solution. Let me give you one simple example. You can see the idea. All right. That equation we learned before. That equation called the logistic equation. Remember logistic equation? All right. That's the Y prime, first order, ODE. Two terms, right hand side. Capital A constant times Y minus capital B minus Y squared. Okay? So this is the logistic equation. This equation, so we solved it before. Okay? So here I just copied the general solution. So we have a general solution. All right. So general solution. Y equals A. so it's a fraction, numerator constant a. Denominator, there's a little c constant times negative at plus b. Yeah, something like this, okay? Yeah, so that's the general solution. Capital AB both given constant, but this c is a parameter. C can change, okay? Yeah, arbitrary constant c you can use. So you have the general solution, all right? Yeah. But if you look at the original ODE, the logistic equation, you can see y equals 0 is also a solution, right? Yeah, because y prime, left-hand side, 0, right-hand side, a times 0, b times 0. Y equals 0 means y equals constant 0. Y identical to 0. Y identical to 0 constant. Yeah, everywhere. This function is another solution. But this function is not covered by the general solution, right? Yeah. From the general solution, it can never be 0, right? Yeah. Because numerator constant a, we assume a is non-zero. A is non-zero, okay? Yeah. So in the logistic equation, a cannot be 0, right? Yeah. Yeah. So then the general solution can never be 0. Yeah. That means this solution is a singular solution. Okay? Yeah, singular solution. Yeah. So that's the concept. All right? Yeah. Now, you understand this concept better. Yeah. Singular solution concept better. Now let's understand for this system, non-homogeneous second order linear ODE. All right. A general solution, here. So here we talk, so the general solution here, non-homogeneous, right? So here we talk about the non-homogeneous system. So what we are talking about is the general solution is in this format. Okay? Yeah, YH part plus YP part. Yeah. Yeah. All right. So that general solution covers all solutions of this ODE. It does not miss any solution. So that general solution, if this kind of general solution covers all the possible solutions, that means no singular solution. Yeah. Because if there is a singular solution, the general solution cannot cover singular solution, right? By the definition of singular solution. Yeah. So that means, yeah, after you find the solution in this form, yeah, so you know you do not miss any solution. Yeah? Yeah. All right. Then, next question. How to find a solution YP, particular solution? Yeah? Right. Yeah. Two methods. Yeah. Yeah. All right. One simpler, the other more general. Yeah. 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 But we need to learn these methods. All right. The first method, method of undetermined coefficients. Yeah. So this idea is very useful. Method of undetermined coefficients. Yeah. So we use we need to choose some appropriate coefficients. But when we choose, we don't know what they are. Yeah, we don't know. But we need to derive those coefficients. So we call it undeterminate. We need to do calculation to find those appropriate coefficients. Yeah. So that method, so we call it, yeah. It's a, not too hard, yeah. Yeah, but the idea, pretty simple, yeah, but pretty effective. Yeah. All right. Here, yeah, for our previous system, for constant coefficients. Yeah. Yeah. Because for non-constant, too complicated. Yeah. Non-constant, too complicated. Yeah. Constant, much easier. Yeah. All right. Simplified form. Yeah. So this form. This form, remember, yeah, the damping system first, right? With external force. Yeah. So that's what we need to solve. Yeah, in the previous topic. Yeah. So, yeah. All right. A and B are constant. Yeah. All right. Then, so here, in order to solve this system, we need to consider what kind of functions the little r function could be used. Yeah. So there are several interesting choices here. Several interesting choices for r function. Yeah. The first special case, r function is an exponential function, e function. Yeah, e to the some constant times t, yeah, or x. Yeah. E function, exponential function. The second, power of x function. Yeah. Yeah. Another commonly used case, cosine or sine function. Yeah. Commonly used choices for r functions. Or sums, yeah, because that's the basic building block, right? Yeah. You treat these three types of function basic building blocks, and you can include several blocks, right, in certain forms. Sums of these functions or product of such functions. Yeah? Yeah. So typically, we consider r function with the structure described here. Yeah. Yeah. So then, if our second order linear ODE, follows this pattern, so we have way to solve it. We can apply this method of undeterminate coefficient to solve it. Okay? Yeah. Yeah. All right. But there is some technical consideration. Yeah. To find such solutions, may not be that obvious. Yeah. Because the problem is there is a problem. Yeah. Because when you represent, so first you need to, when you use this method, you need to represent the structure of the solution. That structure of the solution is important for this method. So you need to find a way to represent the structure of the solutions. Okay, there is one critical. This is the critical step. Yeah. When you represent the structure of the solutions, you need to use undetermined coefficients. Yeah. Okay. Yeah. Because sum or product. Yeah. So in each block, you need to use certain undetermined constant. Capital A, capital B, capital C. Yeah. So you need to find out those constants from your system. Yeah. Later, in our second half, I will show you example. Yeah. But the hard part is how do you represent the structure of solutions correctly? Yeah. Correctly. Yeah. Yeah. There is a theorem. So there is a theorem regarding the structure part. Yeah. So it's called a choice theorem. Yeah. When you make your choice, yeah, there are certain rules. Okay. Rule number 1, number 2, number 3. Yeah. So that theorem pretty long. Okay. Yeah. 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 But we will learn. Yeah. The choice theorem. Yeah. Okay. Yeah. So then you can represent the structure correctly by that choice theorem. Represent it correctly. Yeah. If the structure is wrong, you cannot find a solution. No. No. You cannot determine those coefficients because the structure completely wrong. Right. So you have to, the first step, you have to make your structure right, based on that choice theorem. Yeah. So there are 3 rules. Yeah. Yeah. So we will carefully apply one of the 3 rules. Yeah. Based on the cases. Based on the cases of the form of the ODE. Yeah. So then we can determine appropriate coefficients and find that YP solution, right? Our goal. We want to find a YP solution, particular solution. Because homogeneous YH solution, for this equation, we have confidence to find a YH solution, right? Yeah. The formula given. Yeah, but the YP part, yeah. So we need to do a lot of work to find a YP solution. Then we get a whole general solution. Okay? All right. Let's take a break. Yeah. So when you come back a little after 7:10, yeah. So we will start the second half.